I will be talking about my project that I started a couple of months ago, and now I'm kind of happy and satisfied with its current beta state or alpha state, so I can present what it can do. The main goal of this project is to generate code for Scala functions based on their types. So I want to do a lot of live coding to illustrate how this works. And the main thing that it uses is the CurryHoward correspondence. So I'd like to ask you, how many of you don't know enough about CurryHoward correspondence to understand why it could be useful for generating code from types? Okay. So I will give an introduction to CurryHoward correspondence. So that was about half of the people. So let me then start with introduction to what CurryHoward correspondence is. When we have code in the program, so I needed to also ask how many people are familiar with Scala. So pretty much everyone except 3 people. Oh, you as well? 2 people. All right, so this will be, all examples will be in Scala, but hopefully easy enough to understand for people familiar with functional programming. So suppose you have code like this in your program. So that means that at some, well, assuming that this code compiles and runs, of course, this means you have been able to compute a value of type t in this program, in this place. So this is a proposition that your program can compute, or your code has value of type t. And let's denote this proposition by ch of t. So that means code has value of type t. Doesn't matter which value, just some value of type t. Now this proposition could be true or false for a given program and for a given type t, because your program might not be able to compute values of certain types because those need some other values of some other types and the program doesn't get them. So this could be true or false. Now, the CurryHoward correspondence is this correspondence between types and propositions. So types such as integer, float, array of integer, and other types like this corresponds to propositions. Code has value of this type. Now, these propositions could be true or false for a given type and for a given program. So here's an illustration of why this correspondence is interesting and productive. So the reason is that if you have types like you have in most functional languages, like in Scala, you have a tuple type. If your program has computed a tuple type, AB, it means that you have computed the value of A, and also you have computed the value of B. Otherwise, you cannot make a tuple type. Now, if you translate that into propositions, it becomes that you have ch of A, and also you have ch of B. So this becomes a logical conjunction of the 2 propositions. So in this table, I have summarized what happens. So on the left, you have Scala syntax of different types. These are type expressions. And here there are logical propositions or formulas in the logic. And here there are the same formulas, but in the short notation. If you have an either of AB, that means you have computed an A maybe, or maybe a B, but you don't know which necessarily. So it means in the logic that the proposition ch of A or the proposition ch of B are true. Now, if you have a function from A to B in your Scala code, that doesn't really mean you have an A or that you have a B. But it means that if somebody were to give you an A, value of type A, and you would be able to apply that function and produce a value of type B. Which means that if ch of A is true, then ch of B is true. So this is an implication in the logic. Finally, the unit type can always be computed. It does not need any other data to be computed. So this corresponds to a proposition that is always true for every program. It is a true proposition, identically true. And the nothing type is a type that you cannot compute. You can never compute a value of this type. So that is a proposition CH of nothing is identically false in all programs. So now you see that different types in Scala or in another functional language, for that matter, most of today's functional languages have the same constructions of product, sum or disjunction, implication or function type, unit, and nothing. So in the logic, these are the basic fundamental logical operations. And so because you have all of these operations in the logic and in your program, it means that any logical formula corresponds to some type, and any type corresponds to some logical formula. So in this way, you have a one-to-one correspondence of a sort, where you have formulas in the logic and types in the program. And when you have a certain formula, which could be much more complicated than just this, it corresponds to a type expression that could be much more complicated than this. Now, I use a short notation, which I want to talk about briefly. So what is this short notation? Well, I use logical symbols like conjunction and sorry, I'm in your way, right?
It's fine. I can look around the side. Don't worry about me.
I'm sorry about that. So conjunction is usually denoted like this. Now, I also use this symbol, which is a product. Disjunction is denoted like this. I also use the symbol plus. And I prefer to use the plus and product when I talk about types, and the conjunction and disjunction when I talk about logical formulas. Implication is like this. True is 1, false is 0. So this would be the short notation for the types. Now in Scala you also can have type parameters. Now type parameters in logic means that something is true for any type t. So for any proposition t, some formula is true. And here's an example. Imagine this function, which is to duplicate a value. So you take a value of type A and you return a tuple of AA by simply repeating this value twice. Now, in the logic, the type of this function corresponds to this formula. For all A, from A follows A and A. Now, this is a true formula. This is a theorem. It is true that for all A, if A is true, then A and A also is true. So that's not a very interesting, perhaps, theorem, but it is valid, it is true. And so you see, you can write code of this function, and that corresponds to a true theorem. And in fact, this is generally true. So this is the first thing that we notice, is that any valid theorem, any formula that is a theorem, corresponds to some type that can be implemented. So here are some examples. For all A, from A follows A. Now this is obviously true. Well, this is an axiom in the logic in any case. And this corresponds to the identity function, which takes a value x of type A and returns the same value x. So the type of this function is A to A for all A. Another example is from A to true. Now this is taking any value of type A, returning unit. Well, not a very interesting function, but nevertheless, here's a more interesting one, perhaps, from A to A plus B. Now this is taking an A and returning an either of A, B. So then, obviously, you cannot make a B out of A, so you must return the left always, but so what? You are satisfying the type. So that's it. Here another one is taking a tuple of AB, returning A, so that is just taking the first element of the tuple. And here's another one, taking an A and returning a function from B to A. Now this is a little more interesting. It's the function that takes an A, returns a function that takes any kind of B, any kind of Y of type B, and ignores that Y, and returns the X that was given initially. So that is a higher order function, or if you prefer, a curried function. But again, so we have this logical formula that is true, and we have a function that can be implemented. And most interestingly, if you have a formula that is not true, you cannot implement its type. So here's an example. For all A, from 1 follows A. Well, that is obviously not true, because what if A is false? It cannot follow from truth. Now, try to produce a code in Scala that takes a unit as an argument and returns arbitrary A. You can't. There's no way to make it. You don't know what the type A is, so you can't make it. Another example, from A plus B into A. So from the either type, either A, B, produce an A. You again cannot do this, because what if this either doesn't contain an A, it contains a B? So there's no way to do it. Another is from A, produce A times B. Again, impossible. Another one is from A to B, produce A. This is a bit more difficult to understand maybe, but you don't have an A still. You have a function from A to B. So you're trying to wait for somebody to give you an A, but nobody's going to give you an A. And you're required to produce an A yourself, and you can't. So these are invalid formulas or non-theorems that you cannot derive in the logic, and at the same time, these are types of functions that you cannot implement. So then there is this interesting correspondence that not only types correspond to formulas in some nebulous logic, but if you can prove the formula to be true, to be a true theorem, then you can write code for the function. And if you cannot write code for the function, you cannot write the proof of the formula, and vice versa. If you cannot prove the formula, then you cannot write the code for the function. So these are equivalent. So this is a second side of the correspondence. Not only that types correspond to formulas, but proofs of the formulas correspond to code. Well, so far we haven't seen how it works. We will see it a bit later in this presentation. So there's a natural question that is, if I give you a type or a formula, how can you implement it in code? Here's an example. Okay, here it is. All right. So go ahead and write code for this function. It's not obvious. So how can we decide? How can we decide that this is even possible? And since I know this, I've gone through this. If you just substitute one of these A's by a B, it becomes impossible. So again, why? So how do you know this? So luckily, there exists an algorithm for deciding this. So this logic in which I'm working, I did not talk very much about the logic so far, I will. It's called intuitionistic propositional logic, which has a decision procedure. In other words, there's an algorithm that takes a formula in this logic as a symbolic expression and does some computation on that symbolic expression and decides whether you can prove it. And if so, produces a proof. And if not, then it shows you why you cannot prove it. It's not just that you couldn't manage to prove it, but you actually know that it's impossible. So it's a real complete decision procedure. The byproduct of this decision procedure is that you have proof for the formula that can be translated into code for your function. And I will show how that works. But first, let us have a little practice maybe implementing code from types. I will go through this very quickly. I'm using the Ammonite shell, which is very nice because I can very easily import libraries from Maven. for example, this line, import $blah, blah, 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 it will download, if necessary, a library from the Maven repository with this Scala version and so on, and at the same time will import symbols from that library. So I already have it in the cache, so it doesn't have to download, but it will if necessary. So the first example is that we want to implement this function of this type. So let's see. I need type parameters A, B, E, and I need to implement this function. So how would I implement this function? Well, let me edit this a little for readability. Copying from PDF. Okay, now it's more readable. So how do I implement this function? Well, obviously, I'm supposed to produce a function from this E to A. So let's produce that. So this will be of type E to A. Then I'm supposed to produce a function from A to B to something. Okay, let's write that. And then I'm supposed to produce a function from E to B. Okay, from E. And now I'm supposed to produce a B. If I can produce a value of type B right now in this line, I'm done. How do I make a B? Well, I don't have a B. But I have A to B. If I could produce an A, I would use this A, B on this A, and I'll have a B. How do I get an A? Well, I don't have an A, but I have an E to A. So I can use E to A on something of type E to get an A. Well, where is something of type E? I have it. It's right here. So now I'm done. So this is the way I write code. So this, some people say this is type-directed programming, where you start with types that you need and you kind of derive what the code must be. So let's look at the second example. Now here, if I wanted to implement this, I would do the same thing. I need an A. I don't have an A, and I have E to A. I would have to apply E to A to something, but I don't have an E. I have an E to F, and I'm stuck. So in this example, I'm stuck trying to get a value of type F, for which I need an E, and then I can't get it. And the third example is to implement this, which is a map function for the option. So let's call it map option. So here, what can I do? Well, obviously, I get an option, so let's call it OA. I have an AB, and then what? I can match on OA, and I have two cases, so sum of some X. So that is of type A. Now I can use AB of this A. I got a B, I put it into a sum, then I get an option B. And then obviously case none goes to none.
Maybe
sorry, you're right, there was an X. Nice editor. So now note I could do it in a different way. I could just here return none and ignore that stuff. And that also has this right type. It compiles. But it's a kind of useless function. I ignored all my arguments and I just return none always. It's kind of useless. And also it loses information. So I had information, I just ignored it. So looking at these examples, we see two things. First of all, often there's just one useful implementation. Just look at the type and you have one implementation. And sometimes you have none. And sometimes you have more, but one of them is more useful than others because it doesn't lose information. So why do you want to not lose information? Well, if you're familiar with what the map function is supposed to do. How many of you know what that should be? Yeah, pretty much everybody. If you know what the map function should do, it shouldn't lose information. It should satisfy equations such as identity law. And if it loses information, you won't satisfy identity law or composition law. And so, obviously, functions like something that always returns none wouldn't be very useful for those applications. So if there's only one implementation, why don't I use the computer to give it to me? Why do I have to do this? I mean, it looks like I'm just following the type. I have no freedom, and I'm just doing my motions. And why do I do this? So why don't I just, click a button, and that's what I can do. Indeed, here's a line. All right, I just do this. Let's copy this over there. Done. Same thing. You can use it. This map, you can use it. Like val reader A int to string equals to string plus ABC. All right. What is RA of 1 to 3 is correct. Now let's map this from integer to Boolean. Okay, and it's the map of reader A and the function. Well, let's call this map of function from integer from string to Boolean, right? And this function from string to Boolean. Where would it be? Like it would be S. Starts with 1, let's say. Let's call this. Okay, we got something, right? It's an integer to Boolean now. Let's apply this res9, right? The res9, which I got right here. Let's apply this res9 to this. What do we get? It's true, because that started with 1, right? So it works. What did I do? I just said implement right here. I write the type of my function and I say implement. That's all. So that's one interface, one API that the library provides. Another API is called Offtype. So this is an illustration of Offtype. Now Offtype is different because it can have extra arguments. So here's the situation. You have a case class which has an int and a string. And you're supposed to produce a value of this case class. And you're given f, which is a function of funny type signature from string to Boolean to int. You're given a string, and you're given a Boolean, and you're given an f. So how do you get result out of it? Well, let's find out. For result, you need an integer and a string. Well, we already have a string. How do we get an integer? Well, we need a string and a Boolean to get an integer. So we have a string already. And we have a Boolean. Excellent. So we can just juggle them together and call the function and the right arguments somehow and get the case class that we want. And that's what it does. So it's deriving, it's a shortcut to first defining a function from all these types to result and then calling that function on these arguments. So it's a shortcut to saying first, define some auxiliary function of type string, then this, and then Boolean to result equals implement, and then call that function on these 3 values. So instead of writing that, if you just want it once in an expression, so you don't want to define functions that you would use many times. You just need an expression in the middle of your code. Then you just say Offtype. You know you can get it from other things. So you just say what type you want and from what things you want to get it. And you can use Offtype without arguments too, if that works. Let me try, for example, like this. Okay, so I get id_int, which is an identity of type integer to integer, I hope. So why identity? Well, what other function are we going to have? So CurryHoward library treats all types as type parameters. It doesn't know anything about integers, about strings, or booleans. So just give it an integer, that's just a fancy name for some type parameter. And so it won't produce anything except an identity function in this example. And that's probably what you wanted. So, I mean, if you're telling me the type is integer to integer, how am I to guess what you want? There are so many functions from integer to integer. Question?
I'm just curious, what happens if you run it with like a really complicated type from like a real-world library, like maybe like instead of type of type, then like the spray JSON types or something? It would still do the same thing?
So I think so. It's just that if it's identity, it will note that they're identical types. If it's a complicated type, it won't try to think about it. But maybe that's what you want. So, like, let me see. Future of sequence of try of string. 1, 2, 3, 4. Yeah, going to future of sequence of try of string 1, 2, 3, 4. Poof. What happened? Yes. Future Scala util try. All right. Let's try again. Something is wrong.
Maybe the REPL doesn't like do the use.
No, it does. Where is the future? It did input, right? What is not found exactly? Type. Oh. Future. I'm not sure what that means really. Not found? What exactly is not found? Future of sequence of...
You're missing a square bracket on the left side of the type.
Am I?
Should be 4.
Am I?
1. Future.
1.
The whole thing is supposed to be inside the
So 3.
So, yeah.
3. No, I don't think I'm missing.
Oh, never mind.
Yeah. Something else is wrong. Well, it's a typical demo effect. Something else. Why is it not finding type future? Sorry, what is this?
Does it understand sequence?
Sorry?
Does it understand sequence? Is that in the standard namespace?
Let me get rid of the future. Let me just... Sorry? What?
What happens if you try future string to future string?
Yes, I will try that.
Maybe you can't find the try and in the future was okay.
Let me try just sequence string to sequence string first. Something is fishy here. It can't find types.
You need like Scala collection sequence or something.
Scala collection
I don't know where it is.
sequence. No. All right. I will have to investigate this,
Try
but
qualifying it.
sorry.
Try qualifying sequence.
How? Like writing up exactly this. But it found it. It says it can't find.
Does it definitely work with parameterized types? Like if you did it with type variables, you type f of string to f of string, does that work?
F has to be defined.
I guess we should.
Okay, I don't know why, but sometimes things don't work in Ammonite that work in actual compiler. I will find out. This is perhaps too ambitious for this demo. But certainly parameterized types work if you define them. Let me see. This certainly works. For example, like this. And then I want to define map on this, which is, let's say, R of t, t, u, RU implement. Done. And let me see if Offtype works. Offtype of this works. And look at what it said, returning term, right? So this is a lambda-calculus term that it returns. So that is a hint about what's going on here. So what's happening is that so this macro, this is a macro, this is a macro, Offtype and implement are macros. They examine your type that you're given as a syntax tree, as a type expression, and they then convert that to a logic formula and try to find a proof of that logic formula using the logical rules of derivation and logical axioms. And when the proof is found, they convert the proof back into code using lambda-calculus. So how many of you are familiar with lambda-calculus? Quite a few people, almost everyone. So in the library, the features right now are implemented are that I support all the standard types, case classes, function types, type parameters. I support type aliases, constant types are supported, and if there are several implementations available, like for example, option to option, option A to option A, right? So what option A to option A should be an identity. If you generate a function of type option A to option A, that should be an identity. So that's could be seen as some kind of heuristic, which is that tries to find out what is the best intention for your function to be. So here's a bunch more examples. So for example, you can implement the distributive law, which is the isomorphism between these two types written in a short notation. Now you see why I prefer to use arithmetic notation for types rather than logical notation, because then it becomes obvious what that means. It's just an arithmetic identity for the type cardinalities. And obviously, if this is true, then types are isomorphic and vice versa. Now, if you write this in a logical notation, it becomes a jumble of wedges and inverted wedges, which you have to unjumble, and that's confusing. So implementing these isomorphisms is a breeze. You just write these types like either A, B, comma C as a tuple going to either of tuple AC, tuple BC equals implement, done. So types like this work very well. What doesn't work very well right now is, well, you have seen maybe some more complicated things with library types. Also, what doesn't work very well is when you have a lot of nested options in your type, like option of option of option of option of option, going to something. There's so many different ways in which to ignore things there, to take a none out of here, to take a none out of here. And it's very hard to, first of all, to enumerate all the possible proofs. It can take a while, becomes slow. And then to choose the one that is the best, that becomes a difficult problem. And sometimes it fails on other examples like this. So another example that is questionable is tuple AA to tuple AA. So did you want to preserve the order or not? The type doesn't tell you this. So these are ambiguous things. So as you realize, types are not enough to specify code. In some cases, they are. In those cases, you just say equals implement and you're done. And if you don't have a proof, well, let's implement this. Suppose I made this attempt to implement this. Type parameters are AEF equals implement. Poof, cannot be implemented, it says. Now, cannot be implemented means that it has proved that there is no implementation. This type is not inhabited, and you cannot possibly write code of this type. So there's no, it's not that, you know, I told you, well, I can't come up with an E to substitute into something, right? Maybe I'm not clever enough. How do I know? No, actually, that's not true. There is no implementation. So there's a certainty here. It's an exhaustive proof search.
But what will it try to do in the tuple of A to tuple of A example you mentioned? Will it just end up doing identity, or will it tell you I can't make an intelligent decision?
Let's see. No, it will give an identity function, I hope. Yes.
How does it choose that over swap?
So actually, okay. So actually, I expected it to work, but it didn't. So it says that it can be implemented in two inequivalent ways, and it has a score, which is a heuristic, and the score is equal for these two. So I've played quite a long time with these scores and how to figure out. So your question was, how does it choose which one if there are several? Now, obviously, it doesn't know what you want. So there are ways of going around this, and one way is to say, give me all of these, and then I'll run some runtime tests and choose what I want. And so that's another thing that you can do. In fact, that's available right now as an API called Offtype. And Offtype gives you a sequence of two functions which implement the two possibilities. And if you want to choose between them based on whatever requirements you have, then you can do it at runtime. I haven't yet figured out how to do this at compile time.
Why are the two cases where you take the first term and return twice and the second term twice?
So the question is, why didn't it consider ignoring one of the tuple elements and returning the other one twice? The answer is that loses information. So that has a higher information loss score. This score is information loss. So it's more lossy because you ignore part of what you're given. And this doesn't ignore it. So another part of score that I implemented, but maybe this is, I'm not sure, it's not doing what I expected, but I played with it, that it tries to preserve the ordering of things in tuples. Now, this may not be what you want. I'm not sure it's a good heuristic, but it sounded good at the time when I was implementing it. Anyway, I have a lot of tests for this library, and in the tests I implement a lot of monadic functions like flatMap and map and so on for a bunch of standard monads like state, continuation, reader, and all of that just works because the types are very tight. They are constraining very highly. So I'm not going to show you test code right now, but you're welcome to check it out. It's basically writing down the type signature and saying equals implement. So you can easily imagine what that is like. And then, of course, you can check laws using Scala check at runtime if you want. Now, I will show you an experimental API where I actually get lambda terms out of these, and I can do symbolic checking, which might be interesting to many of you here, because that's kind of already getting to the point where we can do interesting things, even though it's still at runtime. So very briefly, how this all works. So the logic is represented by rules of derivation and axioms. Now, in this presentation of logic, I just have rules of derivation. I don't have axioms. And the rules are written in this notation, the strange thing here, sequence. So these are called sequence. So this is a sequent. So what is a sequent? It is a number of formulas on the left. Then there's this turnstile symbol, and then there's a number of formulas on. There's one formula on the right in this logic. So formulas to the left are premises. This is what we assume to be already proved. So each of the formulas on the left are already proved, and on the right is what we want to prove. And so the sequent is a proof task of sorts. And each rule here looks like this fraction with something in the numerator and something in the denominator. To the right of the fraction is just a name. So this R implication or left implication, right implication, these are just names. You don't do anything. They're just labels to say which rule I'm talking about. But the rule is this fraction. So in the numerator, there's one or more sequence. In the denominator, there's one sequent. So what does it mean? It means if the sequence at the top are already proved, then you can prove the sequent at the bottom. So logic is specified by giving you a number of these rules. And then some of these rules have nothing at top. And like the first two rules here, they have nothing at top. And so they are axioms. They give you something you can prove with no premises. With no previous sequence. Premises, you always have premises. Although here you can prove truth with no premises. So gamma is anything. Gamma is kind of notation for any number, 0 or more premises. So this is gamma. Now, this notation is extremely dense. So there are all these conventions, like what is gamma, and what are these things on top, and so on. Extremely dense notation that is very hard to read and to write. Yes?
What is it necessary to write gamma in all these cases? It looks like pretty much every single one has gamma in it.
Yes. So it is necessary because you need to say that, for example, here's an example. You want to prove that A or B is true. And for this, you need to prove this and this. So in both of them, you can use the premises from here. So you show that you take some premises and you duplicate them over here. So if you remove gamma, then it would not be clear that this sequence at the bottom has actually different premises. It can have one or more different premises. Or the sequence in this rule. Here you say, if you want to prove this, then you should have proved this and this. And gamma is repeated. So the fact that it is repeated is important. You're showing which premises you're copying from one sequence to another, and which premises you're not copying. You're replacing them with new premises. So that's why gamma is written. And there might be a sequence where you take something out of gamma and replace it or not, and so on. So that's why it's written. So basically, gamma stands for one or more arbitrary premises. The way we use this to prove things is we start from the bottom to top, from the bottom of each rule. So we say we have a formula, and this formula has. Here's an example. We want to prove this formula. Okay, which means that we have no premises. So we have an empty set. So gamma is an empty set. So I write an empty set to the left. And then we want to prove this. So how do we prove this? Well, we look at what rules would apply. So we do bottom up. We look at each rule. At the bottom of each rule, there is something that we can prove if something else were to be proved. So which rule matches this at the bottom? Now it is this rule, the right implication, which means there's an implication at the right of the sequent. So we use that rule. So here's a proof. We take the first sequent, which is this sequent, and we apply the rule right implication. So right implication means now we have to prove this gamma comma A goes to B. What is A and B? Well, A is this R to R to Q, and B is Q. So then we have the sequence R to R to Q, goes to Q. And so now we look at sequence S1. So what rules apply to it? Well, the rule left implication applies to it. Because now left implication is the only rule that can do something when you have a premise on the left that has an implication. Now I put this in blue. So in blue are the interesting parts. And you match on what is on the left with the blue or on the right with the blue. So you apply the rule left implication and you get two sequence, because this rule it requires you to prove two sequence. Now if you put B and C where they belong, then B is R to R or Q or something, C is Q, so you have two sequence. One is Q to Q and one is this. So this is the new sequence S2 and this is a new sequence S3. Now sequence S3 is easy. It just follows from the first axiom, from this. X goes to X with no other premises. So S3 is done, but this one is not done. So what do we do with this? Well, we again, look, what can we apply? Well, we can apply again the left implication. So, because we have an implication on the left. So we get two more sequence, S4 and S5. Now, S5 we might be able to prove, but S4 is again the same sequence as S2, you see? And that's the problem, because we are now going in the circle. To prove S2, we need to prove S2. So we will never get anything in this way. Now we scratch our heads and say we probably need to backtrack now. We didn't do the right rule. Let's try another rule. So we erase what we did. We erase S4 and S5. We're back to here, to S2 and S3. S3 is proven. S2 is not. Now we apply the rule R implication, right implication. So we get a new sequence, and that sequence follows from the identity axiom because it has R and R on both sides, so we ignore all those things and we have proven it. So that's it. So that concludes the proof of the sequence, which is S0 at the top. So this is how it works. So you kind of try to find what rule matches your expression, and each rule decomposes this expression a bit more and gives you more expressions to prove, but these are kind of simpler. They have maybe more parts, but the parts are simpler. And then you again apply, so at each step you decompose things, because if you look at the rules, they're always all of this sort. Each rule has more structure at the bottom than at the top. And yes?
So I'm having a little trouble understanding the syntax for those for that logical language. Is there just one procedure for getting from like the start to finish, or are there different like search algorithms that you could use, and you just chose to use this one?
So okay, yes, I should have said that this set of rules. So the question is there just one algorithm of getting a proof, or there are many? There are many. And actually, it's very hard to come up with a set of rules like this. So there are many equivalent sets of rules like this, and each of them gives rise to a different kind of search tree, because they will decompose in different ways. So each of these sets of rules is called a calculus by logicians. And excuse me. And so this calculus is due to Jensens, and this calculus is proved to be complete and sound. So in other words, using these rules, you prove only the theorems that are valid and all the theorems that are valid. But there are many other equivalent, complete and sound calculi that are more complicated. This is maybe the simplest one for this logic. So this covers all our cases pretty much. Conjunction, disjunction, truth, and implication. So whatever type we have containing disjunction, conjunction, truth, and implication, we can translate this into this notation, and the calculus will give us the proof eventually. Yes.
If we had elimination rules, would the algorithm that you sketched for us terminate?
The question is, if we had elimination rules, will the algorithm terminate? Well, I think we do have elimination rules. Well, we eliminate, for example, here we eliminate implication. Now, the interesting rule is this one, the left implication, which made us suffer because we're in a loop. It does not eliminate implication from the premises. It duplicates the implication and makes you prove something else, again with implication in the left. Now, maybe to try answering your question, I'm far from an expert in the logics, but there are different calculi or sets of these rules, and they're different by the way they treat elimination or other things, and I will actually show one of them. So let me see. Yes, here's one of them, which I'm actually using in the library. I wanted to talk about it a little later, but maybe let me show it right now. So the problem with the Jensens calculus is we have seen it gives us a loop. So we don't know what to do. Maybe we have to try again, because we got a new sequence. So we were in the loop, but we got a new sequence from that loop. So should we try again in the hopes of getting some more sequence, and then finally we somehow get, because we don't know what to do. We were lucky. We got a new rule and we were done. But what if we weren't done trying to use a new rule? Then we have to go again into the loop in hopes that something works, right? So this kind of thing is problematic. It doesn't give us a search tree. It gives us a search graph with a loop in it. And so potentially this is an infinite procedure. We don't know when to stop. So an improvement was done after a long series of works. So it actually literally takes decades to come with a good set of rules like this. As you see, Jensens calculus was proposed in 1935, and then these people published between 1950 and 1990 progressively more clear and more efficient versions of this calculus. So the main idea of this calculus is to get rid of this rule L left elimination, left implication, L implication, because this rule gives you loops. So let's just replace this rule by something else. And the idea of replacing it is that, well, this rule is insufficiently detailed about what kind of implication is on the left-hand side. Let's pattern match on that implication. That implication could be an implication from an atom X, from a variable. It could be an implication from a conjunction, implication from a disjunction, or implication from an implication. There are no other things in your, well, there's also truth. You can have an implication from truth, yes, but that's atomic, let's say. So there's nothing else that you can have in your expression. You can have all these, only four kinds of things. You have atoms, conjunctions, disjunctions, and implications. And so if you pattern match on the left-hand side of the implication here, then you only need 4 rules to replace 1. And if you now choose what's on the top of these rules correctly, then you get a set of derivation rules that are equivalent to what you had before. And that's a really hard part. How do you prove that everything that you prove with the new rules is equivalent to everything that you could prove with the old rules? It looks like a horrible amount of work, and it is. And so they already have done it for us, and all we need to do is to understand their horrible notation. And so if you look at the last rule, well, these rules are kind of easy. Like, well, it's obvious that conjunction of A, B going to C is equivalent to A going to B to C, like curried. That's kind of obvious. The disjunction is also obvious. It's just, A plus B going to C is the same as A going to C and B going to C. That's clear. But the last rule is a real bad guy. I mean, this just, what is this? You got a very interesting syntactic transformation here. You have implication from A to B going to C, and B and C are separated by the parentheses, and here B and C are not separated by parentheses. So somehow, magically, you change the polarity of everything, and somehow it's just, okay? So that is magic. Nobody really knows how to explain why this is correct, and you know, in simple words, why this rule is even working. And the proof I did not check because I'm a working software engineer. I don't have time to learn. I mean, all these things. It takes years. But what I got is that it's based on this key theorem, which is an isomorphism between these two complicated implications, and that is where the B separated from C becomes not separated. So this is in the denominator here, and this is in the numerator here, denominator there. So this is the key theorem, which you can prove, and maybe that convinces you why this rule makes sense. Now, this key theorem is attributed to Vorobyev, who published in some completely obscure place. But here's what I got from a paper by Dikov. And this is this key lemma, which is written in this notation, which is equivalent to what I had on the previous page. And the proof is trivial, as you see. Right, now, so I don't know why it is trivial, but I can give you a stepping stone to proving this, which is trivial, which is this. So this is, yeah, this is really trivial, yes, right? Yeah, the proof is this. So you just write, what is the proof? Now let's understand what it means to have a proof. You write down a function that has this type. That's the proof for the programmers. We're not mathematicians here. So for us, a proof means write a function of this type. And if you can write it, that means that formula is correct. And that's the CurryHoward correspondence. If a formula is correct, you can write code. And if you cannot write code, maybe that's because the formula is not correct, the logical formula. So here is a lambda-calculus notation for a function of this type. It takes an f of type a to b to c. It takes a b of type b, applies f to a function from a to b, which is obtained from b by ignoring its argument. So if you look at this function long enough, you will see this is so. What is this? Okay, let me just make it a little easier to read. Implement. Yes. That's it. A goes to B goes to A of C going to B. So after this trivial proof, let me go back to how we actually get code out of proofs. So I just showed you an easy way of visualizing the proof. Proof is just a function that has this type. But somehow you juggle around all these arguments and put one function into another and so on, and somehow the type comes out right. So that's what it is. So proofs are actually terms in lambda-calculus. And deduction rules, each of these rules actually should come up with a way to write terms. And the way that you can visualize it is that each rule has a proof transformer. So the rule says, if you want to prove this, then you need to prove the two things at top. So, and the rule must come with a function that transforms the two proofs from top into a new proof for the bottom. And this is just an ordinary function, because everything is a function, right? It has type, and so on. You can write code for it. So the proof transformer should be written next to this rule as a function, for this to be computationally reasonable and applicable for us. And I have done that, so, but this is not so difficult. So for example, here's the proof of this expression that we had before, the R to R to Q to Q. The sequence we need to start from the end in order to make the term, because you need to start from the last thing you proved. So the last sequence that we had in our proof was this. The proof of this sequence is the axiom identity, which takes R and returns R and ignores all other arguments. So this is a function which I call T6, which takes arguments RRQ, which is this type R to R to Q, and R. And it ignores this first thing and just returns R. So this function T6 is the proof of this sequence. Okay? Because it has the right type. It has the arguments that are premises of the sequence, and the return is the goal of the sequence. So that's why it's a proof. Now, the next sequence is S2. S2 has this thing, and it was made by rule right implication from T6. So the proof transformer is a function that takes a proof of what was there. So let's look again at this rule, right implication. It's a very simple rule. If you want to prove A to B, then you prove B given A. So what does it mean? It means you have a function that takes A and returns B, and you need a function from A to B. Well, just construct it. A going into f of A. This is a very simple transformation, and so this is what it does. So this is this transformation. So R goes to T6 of RRQ and R. Right. So this is now T2 of type R to R. T2 applied to RRQ is of type R to R. So that is the function from RRQ to R to R, which is this. And so on. So each time you have some sequence, you write down its proof. Either it is from axiom, or it is from another rule, which comes with a proof transformer. So you substitute the previous proofs into the proof transformer, and you have a larger and larger expression. So then this expression grows and grows and grows, and basically you get this. T0 is RRQ going to T1 of RRQ, T1 is this, T3 is that, and then just substitute and substitute and substitute and substitute. You get this huge term. And then you simplify it by evaluation symbolically. You take, this is lambda-calculus term, and you just evaluate it as much as you can. Every time you see a function and there applied to an argument, you substitute that argument. And then you keep doing that until it stops simplifying. So we know that stops once you do it enough times. Once you substitute things enough times, lambda terms stop changing. And so you are at that point, and then that's the result. So final term that my library would give you would be this, after the simplification. But it would go through all those things. It would find, first of all, the proof tree, trying all these rules, and each time you have new sequence. For each new sequence, maybe many more new sequence, and so on. So that becomes a big tree that you have to completely explore to find all the possible proofs. And then you get all the possible terms that prove your formula. And then you simplify them and see which one of them are different. I do alpha conversion, I do beta conversion, I do eta conversion, I do everything. So that they are simplified as much as possible before I decide that I have inequivalent proofs. So, A to A and B to B are the same function, and so on and so on. So all that needs to be done, and that's what is the library right now implementing. And then finally you get your proof term, or maybe more than one. Because you see, there are many choices of what rule to apply. And you can apply this rule and you get a proof, or you can apply that rule, you get another proof. Or you can apply this and this and this, and so on. So the library goes through all of those things. And finally, you get lambda terms. So in order to implement this, you need to take these rules. For each of the rules, you need to write down the proof transformer, which is a function from the proofs of the upper things to the proof of the lower things. And the proof is a lambda term of the right type, and you need to check that the types are correct. And so that's what the library is doing. So finally, let's conclude what we get having this library. Now, usually, you want to have your function with fully parametric type first, so that it doesn't have any specific types, only type parameters. And then you have a better hope of understanding why you want this function and how to use it. And then you can implement it maybe automatically, given its type. When it is trivial to implement, right? Let me give you a trivial function to implement with two parameters, which has type A going to B, going to A, going to A. I'm already missing some parentheses here, right? Going to B, going to B. Oops. Parenthesis missing. Right. Yeah, that kind of trivial function can be implemented. And this is a trivial term that comes out of it. Very obvious. So, another thing that I'm going to show you is that you can symbolically reason about terms. So remember this identity of int that we got? It has a funny type, function1 lambda. And function1 lambda is my subtype of function1, which has lambda terms attached to it. And you can get them. And this is the lambda term in the case class. This is internals of the library, but you could do print, for example, of this. And then you see there's this notation, A of type int, with this funny stuff, going to A. So this symbol C means that this is a primitive kind of, this is a ground type in Scala. This is not a type parameter, but nevertheless it's treated as a type parameter, but it's just, it knows that this is not really a type parameter. It's not a type parameter called int. It's an actual ground type int, and that's why C is there. And if I had a different function, then I would have a different different set of terms. So, and I can reason about these terms. I'll show you a demo if we have time still. So, what is it that we cannot do with this? Well, first of all, in some cases it fails to get a reasonable implementation. It gives you some implementations, but actually I've seen that in some rare cases, none of them are reasonable. It fails to find the one you think it should find, because there are just too many. And in some cases it just works for 10 minutes and then crashes because it's out of memory. Now, the logic is decidable, but it's not easy to decide. It's exponentially hard to decide. So you can write an easy expression that will give you a huge number of possible terms to examine. And especially if you have disjunctions, like option, either. Either is actually not so bad. Option is really bad because it has a none in it. And none is a truth. None is a truth value. So you can always make it. And so if you want to produce a none, then you have lots of ways of producing. You can use this none, or you can use that none, or you can use none of those, or it just explodes. And so I've seen that, and I implemented heuristics to cut it down a bit and sort it in some way, but it's not perfect. So you cannot express more complicated properties. Like if you want to sort arrays, then you cannot express this on these types. Now, many of you know this very well, that you need much more powerful type systems to express such properties as sorting or other things. Another thing you cannot do yet, maybe not at all, is to generate terms that satisfy laws. What I would like very much is to generate type class instances automatically. I started to play with type class instance generation in cats, and it cannot do I started playing with automatic type class generation in cats, but it cannot do function types, for example. So you cannot derive a functor for reader monad because it's a function type. Now, CurryHoward can. So you can automatically derive type class instances, but you cannot automatically prove laws. So here it is. So, for example, okay, let me define a type. Did I define some type already? Like type, yeah. So for this, for example, I want to define a functor instance. Functor R. So this is this R, right? Functor R. So how do I do that? I say new functor R, override def map, AB, and then FA R of A, F A to B, R of B, right? Now, that's what I want to do. Done. Cat's library cannot do this automatically. It can do case classes, but not function types. What I would like is to be able to generate not just the right type, but also guarantee the laws. So if it's a functor or monad or some other thing, I want to specify what that law I want and check it. Right now it's not being checked. So I'm through with my slides. This is the last slide. I'll upload the slides with my bibliography. I want to show you what I can do with lambda terms, just very quickly. Okay, so what is this int? I'm just going to show you very quickly what I want to do with this lambda term. So this is an identity function on integer, right? So I'm going to introduce so I implemented the whole DSL for lambda-calculus. It's very small and very basic type lambda-calculus with very little functionality right now, but basically what I want is to be able to prove laws symbolically. So let me prove symbolically that this is an identity function, okay, on integers. Well, whatever. So how do I prove that symbolically? Well, I want to introduce a term x of type integer, apply that function to the term x, and show that the result is equal to x, syntactically equal to x, right? So that's all I can do. I'm not able to do much more than that. Syntactic equality I can check, but other things I can't really check. So how do I do that? Well, I make an x, which is a variable of type int. So fresh var is a part of a library that generates terms. So this is a lambda term of a simply typed lambda-calculus. The name is automatically generated. This $1 is the name, and the type is the int that I specified here. Then I say id int applying to x. Ooh. Ah, yeah, because id int is my Scala level function, right? I need to get a lambda term out of it. Let me do that. Okay, so now I have an application. Now what is, let me print this. Right, so now I have an application. So there's this term, and it's applied to x. Now I need to simplify this thing, because it's obviously not simplified. Okay, the result is x. So now I want to say that this is equivalent to x, and that's true. All right, so so this is how I can symbolically compute things at runtime. Though this is all at runtime because I got my lambda terms at runtime, not at compile time. At compile time, there was this proof business and so on, but once that's over, I'm at runtime. So now I can run tests and check that this is the function I want. So if I had another example where I get a tuple of AA and I want to transform it to another tuple of AA, and I want to see which one is the right implementation, right? So I want to check identity law for that. So this is how I would do it. So I would introduce, at runtime, I would introduce some values which represent these lambda terms, apply them, simplify, and check. So equiv, this equiv, is syntactic equality. It is just checking. So simplify is this function that tries to apply as much as possible all the rules of lambda-calculus, where you have, for example, here, you have a function that takes an argument of type integer, returns this, and it's applied to this. So if function is applied, that can be simplified. You can substitute this into the body of the function. So all of that is done as much as possible, many times, until it stops changing. And we know this converges, so I don't check anything. Actually, I cut corners here quite a lot because I want it to be not to take so much of my time. But anyway, but this is what I implemented. You can do other things. I just implemented another thing, which is where you have type parameters. It tries to automatically rename them when you apply. And this is a bit of cheating because I have simply typed lambda-calculus, for those of you who know. Right? So I don't actually have universal type quantification at all. I don't actually have type parameters in this calculus. I just have types that are named A or B, and they are parameters, but they're actually not parameters. I don't have quantifiers. And so I cannot express, for example, that this function actually has a quantifier and this doesn't. I can't express that at all. So that needs to be done by hand. So I say, here I can try to show you a last live coding example. Let's define identity on a tuple. Right, so this was AA going to AA. So I do this with Offtype because that's how I get lambda terms right now. AA going to A. Let me actually get rid of this because I have this type right here. Okay. So that fails. I do all of type, and I get a sequence of two terms. So if I do IDT of int, for example, what does that give me? Give me a sequence of two functions. So let me map of getting a lambda term out of here. Now I get a sequence of two lambda terms. Okay, so let me print that. So let me say print of this. Okay, so I have two terms. One is this, which makes me a tuple of A1, A2, and the other makes me a tuple of A2, A1. And they are of type A. So now this type A is a type parameter, but it's only I who knows this. There's no quantifier. So suppose I want to apply this to a tuple. First of all, how would I make a tuple? I need to make a term of type tuple. It's not a Scala tuple, it's a lambda-calculus tuple, right? So that needs a bit of work, so let me try to do that. First of all, I introduce a variable of type, let's say int. Okay? So that's a variable, and it has a type. Now you see this, all this stuff is necessary to represent what it is. Now I want to create values of this type. So how would I do that? Well, I need a value of type int first, right? So let me make, but there aren't any values really, just variables in lambda-calculus. So I need to make a variable. Let me make it xint. Okay, so good. Now I want to make a tuple of xint and let's say yint, actually. Let's take a y. Let's have a tuple of, so I have a t2 of xint and yint. Let's see what that is. So res40 is exactly what I want. Is a tuple of xint and yint. Okay, so now I have a lambda-calculus tuple. Now I can apply this identity function. Now I have a list of two possible candidates for identity function. Let's apply both of them to this. Okay, so let's say it's a map of some I going to I of res40. Now, okay, this doesn't work because I have a function that takes AA and I'm applying it to int, and it's a runtime type error, right? Because type checking is at runtime, because we're doing lambda calculus at runtime. So it must be a function with argument type tuple int, and instead I have a tuple of AA. So to cure this, I introduced extra stuff, which looks like this. So this application with type stuff, and that doesn't work either. Oh, okay. So it tries to unify, but I know why. Of course, I know why this doesn't work. Okay, demo snag solved. All right, demo snag solved. The thing is, I got confused because this is actually Scala type that is different from a tuple AA. This is a function with two arguments. It's a Java style function. So what I should have done is this. A tuple of A is of type, and then I should have done this, you see, with double parentheses on the left. And that's the Scala syntax for a tuple as an argument of functions. If I don't do that, that becomes a Java style argument list. And that's very confusing. But so, okay, but my great and watertight type checking tells me that I cannot unify, and now I understand. So let me do this. Done! So now it works. So it actually has heuristics that showed me that it doesn't want to change the order of things in the tuple. And it returns me this term. Okay, well, I don't believe that this is identity. Okay? I don't believe. I want to check that this is identity. So I get this lambda term, and I apply it with this operator to my res40.
Can you print it too?
Yes. So print what?
Just the lambda term.
Yes. Yes, please. Right. So now if I printed it as 0, for example, lambda term, oops. It's not it's already, yeah. That's the difference. You see, this was a function from tuple AA to A. This is a function from 2 arguments of type A. So that is a Scala snag that got me. Right. So when the CurryHoward library finds that there's a tuple on the left and tuple on the right, then obviously there's some idea that you want to keep the order of things in the tuple, and that's because the order of things in the tuple is information. You don't want to lose that information. So this is my philosophical justification for this. But this is a heuristic, okay? So it doesn't work for Java-style type arguments. Maybe I want to put it there, but maybe not. It's not clear. So far it's not implemented with Java-style type arguments, but it is implemented in tuples. And so, right, so this lambda term is that I want to apply this now to my res40, which I remind you what res40 was, is my tuple of int with x and y. Now I have an application, right? Now I'm going to simplify it, and I get a tuple of, and I want to say this is equivalent res40, true. So I have verified, now you see this extra operator that I had to define, this stuff, right? This extra operator is necessary because I have to tell it that this function has type parameters, and it needs to unify these type parameters with the argument it actually gets. Because it doesn't know that it has to do it. There's no, this is simply type lambda-calculus. So I don't have any representation. And maybe sometimes I want to unify, sometimes I don't. There's no way to decide that in the calculus itself. And so that's why I have to do it by hand. So, all right. So in this way, I can actually reason about the lambda terms that I get from this library. And for example, I have test code in my repository, which I'm encouraging you to check out, that implements map and map functions for some functors, and then checks the law of identity and composition. So it's a symbolic check, right? So it's not just Scala check test with numerical values for int and string. It's actually symbolic check at the lambda-calculus level that the laws hold. So it's a mathematical proof of sorts. So I have this very primitive proof assistant right here that reasons with a very primitive calculus with just a few features, and it has been an enormous amount of fun doing all of this, so thank you. Questions, please. Yes.
The second entry in your bibliography.
Yeah.
With contraction-free sequence calculi.
Yeah.
What's contraction?
I don't know what that is. I tried to learn what contraction is, and I failed. I don't have enough time to study these things, and it wasn't explained clearly enough so that I just understand the idea right away and go on. If I did, I would be able to explain it to you right now, but I don't. Just very roughly what it is that certain rules involve some kind of erasure of certain premises in some ways, and somehow that's or somehow that's bad or whatever. It's some technical term that describes the way the rules manipulate your expressions while you're trying to prove them. So that's what contraction-free means. It's some kind of technical description of rules.
So it's like contraction as in contraction and weakening.
Yes.
which are different properties.
Yes. 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 Contraction as in contraction and weakening. And I have no idea what weakening is either. So, but I've seen that. Yes, I've seen that. Just one of those things. You read the definition, you have no idea what they're talking about. You go on.
So are you using, or do you think you will use like an SMT solver to do the same?
The question is, can I use an SMT solver to do that as a backend instead of rolling out my own prover? I don't know. I think it would be difficult, in part because the search space here is exponential, and I would have to translate that into an SMT language in some way, which is not obvious how to do it. Maybe you can translate that into some huge SMT problem, but I don't know how to do it. There are first-order logic provers, which I briefly looked at, and maybe you can use those. But there are specialized logic provers that do this. Sometimes they use SMT solvers as well, but they're usually different kind of things. So logic provers are usually different from SMT solvers. I don't think you can directly use it. You had a question.
Yeah, so I got that the Jensens calculus was those rules that you had listed there, and then there's also associated with that an algorithm for choosing which rules to apply in which cases, I assume. And is that algorithm something that's canonically associated with the Jensens calculus, or is that something that you kind of derived yourself from the Jensens calculus?
Okay, so the question is, do the rules of the calculus come already with an algorithm about how to apply them, in which order, and so on, or do I have to derive it myself? Mostly they come with algorithm. I just want to repeat that this notation is extremely dense, and a lot of things have to be figured out if you want to write an algorithm for this. But certainly, if you read enough papers, and so I read, that's why I give all these things, all these papers, because they give kind of circumstantial information. Actually, the first paper is the most lacking new stuff. It's mostly pedagogically explaining how we try to implement this stuff, and that's most useful. But it actually doesn't have a very clear presentation of the calculus, but it's more useful for implementing. So one thing that you do is you know that certain rules are always safe to apply. You don't lose anything if you apply them. But other rules are unsafe. If you apply them, you might get into blind alley and you would have to backtrack. So they already know, the logicians already found that certain rules will never lead you astray. You can always apply them, it's fine. But other rules, you have to be able to backtrack from them. Because if you apply this rule and you find no proof, it means you might still find other proofs by applying other rules. But if you apply this surefire rule and you find no proof, then that's it. You're done. There's no proof. So there's this difference between I forgot how they're called, these rules. They're invertible or non-invertible, something like this. So, and they tell you which ones are which. And so, in other words, you know in your algorithm where you need to backtrack and where you don't. And that saves you a bit of time, maybe. But actually, other than that, what I was looking for is an algorithm that's as simple as possible, which means that you just have a bunch of rules. Whatever applies, you try in whatever order. And if it doesn't work, you try something else. If you're stuck, you give up. There's no proof. And whatever you find, also my goal is to find all proofs. And a lot of papers don't want that. They just want to find some proof, especially in logic. Because in logic, they don't really necessarily care, that you interchange the order of some things in a tuple. They don't care about that much, but we do. So I want to find also which rules need to be applied maybe many times to try to find more proofs. And that is not in their papers. But basically, I didn't try too hard to prove anything about what I'm doing. I relied on what they said. So what they said is these are invertible rules, and these are non-invertible rules. And so apply all the invertible rules first. That's what they say in the first paper. You know, apply them first, as much as possible, because you don't lose anything. Apply them, and what are these invertible rules? So for example, these are the stupid rules, like these. You really don't lose anything. With disjunction, the only way to get that disjunction is to be able to prove both parts of it. I mean, there's obviously nothing you lose here. So rules like this are invertible, but rules like that, that's not invertible. You know, that kind of mess, that's not invertible. So messy rules are not invertible, obvious rules are invertible. That's kind of thing.
Okay, well, that's it.
Okay, sorry.
So is your algorithm more or less to do like an exhaustive search of all possible rules that can apply to each position that you're at, and with the exception of doing the invertible rules prior to the other rules?
Right, more or less, yes.
Okay.
So my algorithm is to apply all invertible rules. So I have a table-driven prover. It has a table of rules, and just apply some of them. And then I have a huge list of results, which I'm just flat mapping the hell out of. And then at every possible point, I do simplify, distinct, and then just try to sort by score also. And I don't allow more than 1 million terms, because in my practice that means you're going to crash. And by the way, there's a JVM limit on the amount of JVM code that you can emit for a method. And if your term is too big, you can't even compile it because of JVM limits. So that kind of stuff is, I don't know how to get around that, but maybe you can.
Break it into multiple things.
Yeah, but it's still one method.
Well, but it could be a method that calls.
So you have to break it up into a class, a Java class with methods. Okay, great.
So are you using like Scala meta for the macros? Or
I'm using
regular macros?
plain def macros. Nothing. I don't know about Scala meta, how to use it. I don't know this macro paradise much. I just use plain def macros, plain reflection. I do reflection at compile time, and plain def macros. Take a look at the source code.
Tell me about the score and how you plan to change it. What happens if you do change the score?
Oh yeah, so the question is, what happens if I play around with the heuristics for the information loss score? Does the result change? Oh boy. So I have like 10 different score positions, and most of them are completely useless and screwing up everything if you try to use them. So here's an example. An option of a tuple, right, is a monad. And also you can define filter on it. And so I want to define a function that, okay, define x of a as option of tuple AA. Okay. Now I want x of option A, and I want to transform from x of option A to x of A. A natural transformation. Can be done. And obviously, there's no, you can just do it. Put it in there, all hell breaks loose. There's so many things it can do. There are all these repeated things, repeated option, of tuple of option, of blah, and it just completely blows up. There are hundreds of terms. There's and then I try to put heuristics on it. And I play with heuristics, trying to get the answer I like. I can't, and I'm breaking all my regression tests as well. Why? Here's why. So one heuristic is the ordering of tuple elements must stay the same as, okay? What if you have, how do you know that it stays the same? Well, if you have a term which you put into the second part of the tuple, but it uses the first part of the source tuple, and that's changing the order. But what if this term has 5 nested functions in it? Each of them uses first or second part or something. What do you do then? Well, you add up all these violations together, right? So now your score becomes anything but clear and comprehensible. So now it's adding up together that here you have ignored, you have a case match, right? Match, case, case, case. In this, you have ignored 2 out of 3 of case arguments. But here, you have changed the order in the 2 parts of the tuple. But here, you have a disjunction, and you don't instantiate all possible parts of it. That's also loss of information, right? Because if you want to produce an option as a result, then you better produce sometimes none, sometimes none. Otherwise, you're just not producing enough information. So all of this is score. All of this is added up somehow and sorted up somehow. And once you have a complicated function that has, it has options, tuples, function types, and all that, it becomes a total mess. And then I don't even know if there's finitely many of these terms. I don't even know that. And I'm afraid there isn't in certain cases. And then my search isn't exhaustive, actually. And so I have to somehow think about it, and I was not able to do it. I didn't have enough time to do it. But so short answer is, I have no idea what I'm doing with these heuristics. Looks like I have a big regression suite that kind of works and kind of makes me happy. Right now, my best try is to reason about it on the lambda-calculus level and try to get the answer I want.
How good a heuristic is picking the shortest term or the term with the shortest derivation? Bad.
So, not so good. Because then I would prefer to return none. Right. In most cases. Especially since you want to do this at, you want to prune your tree. You got a million terms. You don't want to look at this, right? So I did this. I don't know how to do it right. I tried this, and the result was that I started returning none a lot of times. Because it's shorter. It's like shorter.
Presumably, I think from this calculus, it's not generally recursive, so you're not going to find anything that's going to potentially loop forever. So if you had, a function that's going to repeatedly recurs to try and, like if you tried to prove like a to either AB to A to B, where you could repeatedly loop on one side, like it's never going to find that because it's not going to recursive.
Okay. So the question is, my calculus is not recursive. So am I ever going to find church numerals or things like this, right? Because church numerals or things that can apply the function many times to the same argument, they are different proofs of the same proposition, or they are different codes that have the same type. The answer is, I'm finding with this calculus, with these rules, Jensen plus this refinement, this is what I'm implementing. Indeed, this calculus is unable to find church numerals or to apply functions many times to the arguments. It is able to find church numerals 0 and 1 only, as far as I can see.
Yeah, I think I was more kind of asking about things that just might never terminate. Because like at the beginning of your talk, you mentioned in Scala, like if you've got a function from A to B, you can't just produce a B magically out of nothing. But technically, you could have an infinite recursive function of any type. But there are other situations where, in theory, you could have an infinite recursion. So, like if you had an A to either AB, and you wanted to make an A to B, you could repeatedly call that function where if you get a B, you return the B. If you get an A, you recurse.
Right.
And that's something that, in certain situations, could be useful, but it's kind of not really helpful under that kind of calculus.
Right. So the question is, what if I wanted to implement a function that is actually partial, but looks like it's a total function because it has recursive calls that actually never return, but maybe in a lazy language that's okay.
And they might return, you just can't prove it.
Oh, well, yeah. So, okay. So certainly in this calculus will never generate them because this calculus is not recursive. So I can't even generate inductive stuff like map on a list. I can't generate that. I do have a kind of stopgap for recursive types. So recursive types are supported. Let me try to demo this. Sealed. Well, let's do a list, okay? List of. Well, let's do a int. I'm going to list of int. Okay. It works. It gives you an empty list. Now, the only way it would give you an empty list is if it went into the recursive definition of list exactly as many times as necessary and not more. And I don't know how to do that. But so you see, it knows what to do, kind of in some situations. But unfortunately, yes. So the calculus is not recursive. It will never generate recursive code. It will ignore recursive types, more or less. It will recognize that recursive types exist, and you have defined them, and you're trying to use them. It will recognize that, but beyond the identity on list int, I don't think it can do much. So I haven't yet figured out how to do proper things on recursive types. I would like to. I'd like to generate maps and flat maps for recursive types.
Would it work if you explicitly passed in fixed point operators?
I need this in the derivation rules. I don't know how I derive things in the logic that has fixed point operators. So if I have a fixed point operator as a derivation rule in my logic, right? That's what I would have to do. I don't know what happens to the calculus. So I'm open to such things, but so far, you see, I'm kind of wary of taking this calculus, which has been analyzed, which people know what it does, and has guarantees, and adding some rules to it. And I have no idea what will happen. And then I might find something, or I might not. I have no idea what's happening. So, since it's a hard question. My next goal is to understand type class derivation. Can I actually do better type class derivation with this? Or it's perhaps a wild goose chase, because you should not do that. You should not just... Type classes are lawful, they have tightly constrained. You should not just take a type and try to derive it. You should maybe do something more intelligent. Recursive types may be the same thing. Maybe you need to understand this is a recursive type, you have to treat it very differently, and not just put a general purpose logic prover and let it crank out. I have no idea. But these logics are not recursive, and I've never seen anything that would suggest that I can use recursion.
Right. What I would say is if you do generate recursive functions, if you want to keep Curry and Howard happy, you are going to have to make sure that those functions terminate. So then you have to add some sort of termination checking mechanism, which is a whole other complication.
Yeah, and that's why I said that general recursion particularly is the one that's going to be tricky.
Indeed, adding a termination condition would mean to put this into an entirely new level of complexity and power. Right now, this, you realize what it can do, what it cannot do. I think this is a nice toy, and I have used this in production. There is exactly one line in production code that calls this implement on a function to create something out of option and type class and case class, and yeah, it works.
What's the context for that one line? Like, what is the actual practical problem with that one line of code?
The practical problem is that I have an option of something with a case class, and I need another case class with an option of something else. And I'm just too lazy. There will be 2 lines to do some option map match blah. All right. Any more questions? Yes.
What is the kind of compilation performance of this compared to like a kind of shapeless style type class derivation? How long does this take to compile?
Depends very much on Depends very much. So the question is how fast it works, right? Well, it depends very much. Here's, okay, I'll give you an example. I, at some point, stumble on a type which is like this. Okay. This type is a functor in A, and we can automatically derive, and it's a monad in A. We can automatically derive interesting flatMap for it, right? So let's see, what is a flatMap for this thing? Is A going to P of B, P of A going to P of B, right? All right. What about we do an option here? Okay. Why did it fail? Because it can be implemented in 4 inequivalent ways. And here are the lambda terms that you are welcome to. Okay? But it took a while. Why? There are actually hundreds of thousands of terms that it has to go through the sequence before it gets to any of these. It's heavily optimized in terms of scores. So it tries to get the best score, and still it takes a while. So that's the compilation performance. It's not great. It's not bad, and easy examples are instantaneous. But once you, I mean, this is particularly nasty. You know, this P is that, right? Just remind you what P is. So when I do a P of option B, there's an option here and an option there. And now I do a flat map on this, right? With an option, 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 option. And you see how many case things. So this is like match, 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 none, 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 match, 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 none, none. So all that has to be manipulated by the prover. And all these, so each time you have a disjunction in the logic, and you branch your tree, you have more sequence to prove, and all that, and you have a lot of those disjunctions. You know, the length of the formula is deceptive, right? Because P has these options twice, and I have P, 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 I have 3 times, so it's geometric, it's exponentially growing. I can write this formula using Scala very quickly, but actually the thing is huge. And so, and it's exponential in the length of the logic formula. So, or maybe even double exponential, I don't know. Don't ask me. You know? So anyway, I just wanted to show you. It works. It gives me something. Maybe some of this is even right. I have no idea. I mean, I don't have any. Once it's like this, I have no assurance that any of this actually has satisfied the laws of flatMap, because obviously there are hundreds of thousands of terms, and some of them are total junk, and they're being chosen on the basis of some heuristics. And what is that? I have no idea. So performance is okay. I mean, I think it's fine. It's not great though, and I wasn't trying to optimize much. I have a bit of a caching, a bit of some shortcuts. I didn't have a lot of effort into. But this example, actually, the first time I ran this, it crashed. It was out of garbage collection limit or something. I had to do more work to get it. So now, for example, when I see a sequent, I put it into a hash map, and if I see it again, I don't try to prove it again. And if I find that a sequent has certain proofs, then I put these proofs in a hash map. So this cuts down the time significantly. But anyway.
Awesome.
All right.
Thank you.
Thank you very much.